Okay, well, thanks for getting up early, everybody. I always knew when I was put down for the 9 o'clock slot after the party the night before that it was going to be quite a hard one to fill. But yeah, I also realised that talking as a biologist and a toxicologist to a room that was full predominantly of earth scientists, along with a number of other disciplines, was perhaps going to be a little bit tricky. And as many of you are aware, plastics have become very topical and they're in the news quite a lot at the moment. And they have been accused of pushing climate change out of the agenda, and that we're spending much too much time considering plastics, which are only a cosmetic issue, and not enough time dealing with the real changes of climate change. So I thought I would perhaps take that up and try and turn that round and show you why, even as climate scientists or earth scientists, it's important to consider what we're doing with plastics and how it might be affecting our future. So I thought it might be useful to just go back to a reminder of what plastics are, because we tend to talk about them as a single thing. We tend to talk about plastics as a single inert entity. And in fact, plastics encompass a whole wide array of different materials. But the important thing I wanted to point out here was that they are all carbon-based, predominantly carbon-based. So plastics are synthetic polymers formed by the condensation of hydrocarbon monomers. And they were first synthesized way over 100 years ago, around about the beginning of the 1900s. And at that time, organic chemistry was in its infancy. And chemists were starting to realize that many of the building blocks of nature were actually made out of hydrocarbon polymers. So things that hold us together, the things like chitin that is in seashells, or the collagen that holds our muscles together, or the keratin in our hair. All of these things are made out of hydrocarbon polymers, and they were starting to learn how to create polymers of their own. They realized that if you took these hydrocarbon monomers and condensed them together, you could make polymers. And the one I've shown you here is the polymer that's used most widely around the world and has been for the last century, and that's polyethylene, made here out of ethylene, which is a petroleum-derived hydrocarbon. But then what we can do with plastics, if we want to turn them into all the myriad of things that we use in our everyday lives, is that we can add additives. And it's currently estimated there are at least 1,000 different additives that we can put into plastics. Sometimes the plastic can be 50, even 80% additive. We put those in there to make those different polymers take on different properties. And we can add colorants and make all these different beautifully colored objects. We can add things to make them harder, to make them softer and more plastic. We can add sunscreens into them so that they can survive in the environment. We can even add antimicrobial agents and other dyes and metals into them to give them different kinds of properties. So whenever we consider the fact that we're throwing lots of plastics into the environment, we have to stop and think, actually, we're throwing highly complex mixtures of different polymers and additives into the environment. And when we first started making polymers, it was all quite quaint. This is a picture of the first mass production unit for plastics. And this is called a bakellizer. And the bakellizer was invented around about the 1930s, and it was designed to enable the company who were making Bakelite, which was the first plastic produced earlier on in the century, in larger vats. And you can see here it's got little openings at the top, and you'd pour in some phenol and you'd pour in some formaldehyde and do a bit of mixing with a catalyst, and out would pop this wonderful material that was called Bakelite. And you can see Bakelite over here. They learned how to add different additives, how to make it paler and darker. And Bakelite is now a collector's item. You can find huge quantities being paid for Bakelite items that were made in the 1930s, things like telephones and doorknobs and other things. And that perhaps tells you something about the durability of the material that we're making. These things made such a long time ago are perfectly workable and still in one piece. So that's where we first started with mass-producing plastics. But to understand why it has become such a compelling issue, we have to move on. Here we go. And we move on 80 years later to the current day, and we find that the production of plastics is very, very different. So plastics, as I said, are made out of petrochemical-derived monomers, by and large. And one of the issues with plastics is that they are intimately linked to the petrochemical industry. So where the petrochemical industry goes, plastics follow, because they essentially use up all of those raw materials produced when we refine petrochemicals, things like ethylene and all of the other monomers, and they turn them into something that is commercially very valuable. So this is one of the petrochemical plants in America that's in a vast valley where there's a great deal of fracking going on. And a lot of these factories have built up, even in the last 20 years, to use the huge increase in the availability of petrochemicals that's come about through fracking and gas shale use. And we're no longer looking at a cottage industry, but we're looking at something that generates massive amounts of material. When I first started talking about the amount of plastic that we were producing about 4 or 5 years ago, it was 300 million tonnes a year. Today, it's 400 million tonnes a year, and it's growing at a huge, alarming rate. So to put that into perspective, if we weighed all of the people on Earth and worked out how much they weighed, they would weigh 300 million tonnes. So every year we're producing 400 million tonnes of plastic, and 50% of that plastic we're designing to use it once and then to throw it away. And the average lifetime of that plastic is about 20 minutes. So you've seen how long the Bakelite items lasted, 80 years later, and they're still perfectly good and they're still collectible. We're using things for 20 minutes, 400 million tonnes produced every year, and then we're throwing them away. And so this gets on to the point that I was trying to make at the start to try and interest earth scientists in the whole issue of plastics, is to try and convert it into the carbon cost or the carbon budget of that plastic on a global scale. This is some data that's been generated comparing the carbon footprint of plastics now and off into the future. And the current estimate is that we use somewhere between 0.86 gigatons of carbon dioxide, or we produce 0.86 gigatons of carbon dioxide a year from the manufacture of plastics and their use throughout their life cycle. Other data has come up with a higher figure of around about 1.8, but somewhere between those two, that's the real figure. And if we want to know how much that equates to, it's about 3.8% of the total carbon emissions on the planet. Now, I am told, I'm not an expert in this, but I'm told that that's about double the aviation industry. I don't know if anybody would care to correct that. So many of us are trying to cut down on our international travel and not go places because we're worried about ruining the planet. And here we are going and buying our sandwiches every day and throwing the plastic wrapper away, contributing twice as much to the global carbon emission. And the other important thing to note from this graph is where we are now and where we're going in the future. Despite the huge topical interest in plastics and all of us talking about different ways of doing things, the plastic industry is in line to exponentially increase in size over the next 20 to 30 years. Those plants are already being built, they're already going into production. Plastic production is increasing. And you can see that if things go on unchanged, we'll be contributing 17%, and suddenly that's a huge contribution to the carbon budget of the planet. So hopefully that has impressed on you that even in terms of climate change, plastic is an important issue and something that we have to tackle. And the other reason that as human beings we have to consider plastic is that it's everywhere. So it's something that's very visible, and it's something that we can see everywhere. And it's everywhere because of those statistics that I've told you about. We're producing these hundreds of millions of tons of plastic items designed to last for, in many cases, many hundreds of years, and we're throwing them away. And under the present way that we use plastic, less than 19% of plastic is recycled. So we all tend to think, well, haven't we solved the problem? We're all recycling things. But in fact, less than 19% on a global scale is recycled. The vast majority is landfilled or incinerated. Landfill it, discard it, don't have the appropriate infrastructure to cope with that, and this is what happens. And this is a picture from Indonesia, where the infrastructure problems that they have dwarf the kinds of problems that we have in this country. But again, as earth scientists, you're interested in all parts of the ocean, and you might think, well, that's a human issue, it's a waste issue, and it's on our doorstep. But we can look around the world and we can find that the plastic has reached everywhere. And this is some data from scientists who have been exploring the Mariana Trench, which is in the Pacific Ocean and is 11 kilometers deep. And this is one of the deep dives that was going down to investigate and to search for new life forms. And one of the things that they found in this search for new life forms was here. This is a plastic carrier bag. So 11 kilometers down in the bottom of the Mariana Trench. And here's a picture that has come from University of Exeter scientists, and this is these teams are associated with Kerry Lewis and some of her wonderful outreach work into the Arctic Ocean. And this is this photograph was taken, I think, around 9 miles south of the North Pole. And this is a picture of a piece of expanded polystyrene sitting on the pristine sea ice at the top of the world, waiting for us to discover it when we go off and have a look. So I think it's true to say that plastic has permeated every part of our planet. Okay, so just because it's there doesn't necessarily mean that it's more than a carbon footprint problem and something that doesn't look very nice. Presumably, if it's not doing any harm, and then we just we could sweep it under the soil, or we could sweep it away and we could not think about it. So things that we throw away into the environment, pollution, is usually only a problem if it causes harm. So what kind of harm might it be doing? Presumably, it's something that's quite safe because we use it in our everyday lives. Well, the issue about why it causes harm is because the things that we thought we would be doing with plastic are not the things that we end up doing with it. When we designed a bottle cap, the designer who made it thought only about its utility on the top of a bottle and how useful it might be. They didn't consider what would happen if it was bobbing around in the ocean. And this is a picture of a fulmar. Fulmars are petrels, and petrels are a kind of bird that skim across the ocean surface, and they pick out fish from the ocean surface, and that's what they feed on. And it's been known for quite some number of years that fulmars are one of the animals on the planet that consume the most plastic. Around about 90% of fulmars will have plastic in their guts if you go and do post-mortem examinations around the coastline. The record for one bird, according to NOAA, is about 84 pieces. And the interesting thing here is that the birds will selectively pick out different colours. So you can find fulmars that have preferentially picked out red or yellow plastics, and you can find fulmars that have preferentially picked out blue. So they're not doing this indiscriminately. They are seeing these things, they're mistaking them for prey, and they're ingesting them. But following ingestion, they're not able to digest or excrete the things that they're swallowing. And what about the effects of large floating items in the oceans? It's been estimated that about 1 million seabirds. Very conservative estimate is that about 100,000 large marine mammals, and that doesn't even take into account things like elasmobranchs and sharks and other creatures, are killed every year due to entanglement in ghost fishing gear and other floating items. I think that's probably a highly conservative estimate, and these are the kinds of things that are very visible. Perhaps something that some of you may have thought of, but to do with the buoyancy of plastics, because they're very light and they're very durable. They can move around on the ocean surface. We know that every single part of the ocean surface is connected with every other part, and the mean time for any one thing to be connected with anything else is about 6 years, if you look at the oceans. And so plastics are moving around on the ocean surface, and they're providing this wonderful opportunity for invasive species to be taken with them on those sort of hydrophobic, attractive surfaces that are offering that site for things to bind to. But in our lab, we've been particularly interested with what happens with plastics when they break up. So you've seen what happens to sand on a beach. You take shells, you take the action of wind and tide, and they break down into smaller and smaller pieces. And essentially in the marine environment, that's what happens. Plastics become embrittled by the effects of UV light. They start breaking up and they break into smaller and smaller pieces. By microplastics, what we're talking about are these small pieces. Generally, we're looking at things that are about less than 5 millimeters in diameter. We're looking at fragments, We have been looking until recently at those items that we deliberately have been adding into shower gels and things that we wash down the sink that now thankfully have been removed from production due to the efforts of ourselves and many other scientists. And we're also talking about fibres. We find many, many fibres in the environment. Let's not forget the artificial textiles, the synthetic textiles that we use in massive quantities and throw out. We're also talking about clothing, textiles and fibres, things from ropes. Smoked cigarette butts, they're one of the most frequently encountered items that we find on the seashore. Smoked cigarette butts are full of cellulose acetate and other biopolymer fibres, so they're also a source of microplastics into the environment. And the reason that we're concerned with these sized items is that many, many marine animals or other aquatic species feed by filter feeding. They don't catch larger prey, they filter organic materials, nutritious particles out of the water column. And unlike the petrels, which are discriminate feeders, most filter feeders are indiscriminate feeders, and they will filter particles out of the water column, irrespective of what they are. If you replace organic matter with a large number of inorganic plastic particles, then filter feeders are highly vulnerable to ingesting them instead. And a lot of the studies that we've done in our laboratories, and this is work of a number of different students, have investigated how those particles are taken up by these filter-feeding organisms, many of which are at the base or the lower end of the aquatic food chain. So very important in transferring things up the food chain and supporting the rest of aquatic life. So this is a little early bivalve larvae called a D-shell larvae. You can see it's got our fluorescent microscopes are showing plastics ingested in its gut. This is a little decapod crustacean. So this is a semi-permanent member of the planktonic community. It will eventually grow into something larger, as will the bivalve larvae. But this is a permanent member of the planktonic community, and this is a copepod. And copepods, one of the most abundant species on the planet, and as most of you will be aware, hugely important in terms of transferring that photosynthetic energy from the sun into, well, most of life on Earth. We've also done studies on organisms higher up the food web. So this is some work from Emily Duncans and Sarah Nelms, two students down in the Cornwall campus. And Emily's been studying marine turtles as they pass across their migratory routes through 3 different world oceans, from the Mediterranean to the Pacific to the Arctic to the Atlantic. And she hasn't found a marine turtle of any species that hasn't got microplastics in its stomach. This is some work from Sarah Nelms, who's been tracking the presence of microplastics in fish and also in the seals that eat the fish, and finding and doing studies to investigate the transfer of plastics from one to the other. And of course, plastics are hydrophobic and they have very many electrostatic properties as well. And these are some studies where we've been looking at the adherence of plastics to the gill structures of animals. These are the gill lamellae of a shore crab. And we can see we can use different imaging techniques. This is a Raman imaging technique to locate the presence of plastics adhered to the gill lamellae and to determine where they're going in the body. It's not going to work. Yes, it is. Okay, so what biological effects, what kinds of things does the ingestion of this kind of plastic do? What might it, how might it affect the different animals that are eating it? One of our study organisms is the lugworm, and most people would say, why are you studying worms? What possible importance could they be in terms of the planet? Well, actually, in terms of sediments and some of the things that we've been talking about in the conference, the oxygenation of sediments and bioturbation, supporting the rest of the aquatic food chain, lugworms are crucially important in that. So they live in burrows and they bioturbate and they ingest sediment, they strip the organic matter out of it, and you see the little casts that they form on the sediment surface afterwards. They're also an incredibly important food item for fish and for wading birds. And this little schematic on the side is designed to show you how vulnerable lugworms are in their little burrows in the sediment to absorption of contaminants from the sediment into their bodies because of the nature of where they live and how they live in those sediments. And we've done a whole series of studies looking at lugworms and trying to understand what effect it might be if they were living in sediments that were contaminated with plastics. Now, bear in mind, some of the sediments that we study and some of the field surveys we've been involved in have found plastics a metre deep in some coastal areas. So we're talking about seriously high levels of contamination of sediments in coastal waters. In this particular study, we were highly conservative and we only added 1% of PVC particles to the sediments that we were culturing the worms in. And what we see happening, again, going back to that carbon budget, this particular picture is showing you that the energy reserves that the worms are able to put on are severely disrupted. So they're not able to put on any weight, they don't put on lipid, and they're growing less well. And all of these things affect the rest of the food web. Again, just to run through this series of 3 experiments, what can also happen here is that the contaminants that are bound to the plastics can leach out of the plastics into the tissues of the worms. And these chemicals here are called phthalates. They're one of the most widely used plasticizing chemicals that we find. And lastly, going back to that example of the adhered pollutants, this is what happens when you culture worms in sediments in which you've added cigarette butts. One cigarette butt can do as much harm to a rock pool of worms as smoking 60 a day can do to a human. It's highly soluble in that environment, and the nicotine can transfer into the bodies of the worm and then be passed up the food web. One final example, and this is the example going back to the carbon budget and emphasising that. We've been studying things that happen in terms of zooplankton. Again, very important in terms of supporting the rest of the food web. And plankton have been estimated to remove about 100 million tonnes of atmospheric carbon a day in the carbon budget. One of our earlier observations, and one which I discussed with Tim quite a few number of years ago now, Tim, was this observation that, of course, what's ingested, quite a lot of the ingested plastic in zooplankton becomes ingested in their faecal pellets. And here you can see some images of that. These are some slightly larger and slightly smaller plastics embedded in those faecal pellets. What many of you will know is that the sinking of zooplankton's faecal pellets is a key part of the biological pump that then pulls carbon from the photic zone at the top of the oceans and pulls it down into the lower oceans. And what these studies are showing is that if you feed small quantities of buoyant plastics, these are polypropylene and polystyrene, in the food of the plankton, then you can change the density of the faecal pellets and you can change the speed at which they sink through the ocean. Why does that matter? Well, it matters because that sinking, as we said, the sinking of zooplankton faecal pellets down into the deeper ocean is pulling a great deal of that carbon and influencing the carbon budget of the ocean. So theoretically, it's been estimated that there are some locations in the ocean where there is 6 times as much plastic as there is zooplankton. Varying estimates occur in different parts of the ocean. But in areas where there are high concentrations, you theoretically could be changing the sinking of carbon into the deep oceans. Okay, so I have to finish up by saying what we could do differently. I can't finish there and just say, well, we're all doomed. We have to think about something positive to go away from this talk with. And of course, there are so many things that we can do differently, and we can do them quite easily. Unlike many other issues, there are a number of different things that we could do. It's been estimated that about 95% of ocean plastics comes through 10 major river systems, many of which happen to be in countries in which there is poor plastic infrastructure. So it's been suggested that if we can concentrate a great deal of our effort into tackling the pollution that's being emanated through those rivers, then we might be able to do something about it. Now, things that address infrastructure are very useful. Things that involve putting large nets across the bottom of the river, which is something that's attracted a great deal of money from various places, are possibly going to be less helpful in the long run. It's also been suggested, well, let's look at all of the things that we throw away and let's target them. There are some things that are entirely useful and we need to use them. And there are some things that we could be targeting. So perhaps we should stop using styrofoam cups. Perhaps we should single out aluminium cans or fishing gear, which could be lasting for many, many years longer than it was ever intended to be used for. If we took out the top 10 items, we could go a distance towards tackling the plastic pollution. And this is data from NOAA on how long many of these items last. It's also, as I said, been suggested that we could put these giant nets around the ocean and scoop up all of the plastic and take it somewhere else. So we could go and clean it up. And I don't know if any of you have thought about the implications of this, but it's a bit like going to your bathtub and switching the bathtub on. And if you want to stop your bathroom from flooding, you go and put a towel on the floor, but you don't go and try and switch the water off first. Unless we go back to the source, we're never going to be able to tackle this problem. We can't just pick it up. We've got to go back and stop the source of the plastic that's coming there. So I wanted to finish up with one of the projects that we've recently had funded from the EPSRC, and this is kind of a bit of a flagship project for the Global Systems Institute, and this is the Exemplar project. What we're building here is a circular economy hub for plastics. And what we're acknowledging is that we cannot solve this problem just by going and picking plastic up off the beach, even though that, causes a relief for a particular location. We have to go right back to the source and work out what it is that we're doing wrong. And it's not plastic that's the problem. We've seen it's highly useful. It's the way that we're using plastic. It's the fact that so little of it is recycled or stopped. It's the fact that so much of it is produced with the sole intention of throwing it away. We can't keep doing that. We've got to circularize the system and not have this linear system of throwing things away. So we're taking a whole range of different approaches in the Exemplar project. We're looking at behaviors, we're looking at the psychology, not just of the consumers who throw things away, but also of the manufacturers who think it's okay to manufacture things that we haven't got any choices over. How can we change those supply chains? How can we make them profitable? How can we decouple plastic production from the petrochemical industry? That's an absolutely crucial thing that we have to be able to do. And one of the ways of doing that is to look at alternative bioplastics, things that don't use petrochemical monomers. And this is an example of some algal-based plastic that's being produced by one of our partners. What are the alternatives? Instead of producing any kinds of packaging, can we go back to doing things in a different way? We used to do it. We used to have milk bottles, and now we have small sachets, and we throw the sachets away. Why do we do it, or couldn't we do it differently? So Exemplar has just started up. It's spanning the whole of the southwest of England, but it's designed to be an example that we might be able to roll out across a more global or an international context. And I think that's all I wanted to say. I'm well over time, and Tim hasn't stopped me, but I'll just finish off with saying I don't even know if we've got time for any questions, Tim, in which case I'll leave it there.
We'll have a few.
Thank you.
That was wonderful. Wonderful tour of plastics tomorrow. We've got a couple of minutes left for questions.
Yeah, great talk. Could you elaborate a little bit at the end of the kinds of properties you might be expecting that might be possible with the algae-based or even wood-based bioplastics, like whether they could be designed to last for a certain amount of time and then be available to organisms as food, or whether there's anything fundamentally different that could be done there other than they wouldn't come from petrochemicals?
I think one of the issues is that there are a number of different approaches that we have to take. So one of the criticisms of recycling is that you've got to have pure materials that are going to last a long time if you want to recycle them. And if we look at the bioplastics, the things that we make out of algae and cornstarch and other things, then by design we want them to break down. But what that means is that we need better infrastructure to be able to separate these streams, because I think we need to take multiple approaches. So with bioplastics, yes, if we could break them down into something that you could then use, that would be wonderful. One of the companies who's been involved with the project, they make seaweed capsules full of drinking water. So instead of buying a plastic bottle, you get one of the seaweed capsules. You drink the water and then you eat the capsule. And so that's the kind of thing. Can we just think completely differently about what we're doing and how we're delivering things?
Great. One more quick question.
80,000 tons of British plastic was taken from local authorities and dumped in Indonesia last year alone. This is because of malregulation by the state. And you didn't mention it, but I do think that the social costs, visiting the social costs of the production of plastic per ton at the source, which is the factories that make it, i.e. the petrochemical plants, would be the most economically efficient, the cheapest and the most effective way of reducing the production of plastic.
Yeah, I totally agree. We make 6 million tonnes of waste a day in the world. If you make that much waste and it's energy rich, you've got a massive opportunity to make money, but you've also got a massive opportunity for fraud. And I'm thinking about some of the recent supplies of recycled material to Indonesia, and they were contaminated with clinical waste, with body parts. You know, all sorts of things have been dumped in what should have been clean recycling waste and sent off because it was going to another country.
I'm afraid we have to leave it there to stay on time. But thank you very much, Tamara. Fantastic opening.